Okay, so let's return the problem of a minus times a minus is a plus, or a plus times a minus is a minus. First of all, a special case, without actually addressing the question directly, a special case of that is this. So minus 1 times a number, let's say 6, but it could be any number, is minus 6. Okay, so minus 1 times a number is the minus of that number. So that's a special case of a minus times a plus is a minus. Or minus 1 times, minus a number is equal to a plus. So, and I guess I'm saying even a bit more than that, because it's the plus of the number you would have gotten if you just multiplied the numbers that were positive. Okay. So this special case, okay, if we were to combine some rules, it would actually imply the general case. Because an even a more special case of this is minus 1 times minus 1 equals plus 1. And then if you had, say, like minus 8 times minus 11, then it would equal to 8 times 11, provided that you assume some extra rules. So you could think of this as minus 1 times 8 times minus 1 times 11 and then, okay, if we're allowed to swap these two numbers, then it would be 8 times minus 1 times minus 1 times 11. And then we said minus 1 times minus 1 was equal to 1. So this would just be 8 times 1 times 11, which is equal to 8 times 11. So I haven't explained why a negative times a negative is a positive, but I have related it to a special case. So instead of the negative of any number times the negative of any number, now it's really just the negative of 1 times any number, as well as sort of the ability to swap numbers when you're timesing. And then you could go on to try to prove that might be the case. And I think that's what essentially some people are doing as well. But I mean, does it really make sense to prove something like this? For example, I mean, does it even make sense that you're allowed to swap two numbers when you're timesing if one of the numbers is sort of like, if it's negative, so if it's like a new number? From the point of view of, so the most common, I think, context when you're actually learning this, you probably learned this in like year 7 or the end of primary school or something like that. At that time, you've just been introduced to a whole lot of positive numbers. Okay, and for you, multiplication and addition were really only defined for positive numbers, but it's really easy to define addition for negative numbers, because negative comes out of the definition of negative is related to the property, like to the addition. But the definition of negatives is not related to multiplication. And if you think of introducing negative numbers as just sort of introducing a new species of animals to your farm, then multiplication might not even really be defined for those numbers and for those between those numbers and your old numbers. So one way to view this problem is you're actually giving a definition of multiplication for negative numbers with other negative numbers and for negative numbers with positive numbers. Okay? So since we haven't dealt with these numbers before and multiplication was only defined on the positive numbers, we can actually use it as a definition. So we can say the negative of a number times the negative of a number is the same as if the numbers were positive times each other. Okay, but that's not the end of the question, okay, because why would you define it that way? Okay, so now we're allowed to say we defined it that way, but what kind of things are we restrained by? So we do have some what guides do we have to make this definition? And so it's not just like an arbitrary random definition. So for one, like something like this that I was trying to do, I was trying to swap the order of multiplication. So hopefully that's a property that I can maintain when defining multiplication with negative numbers. And it certainly is, because all I did was I said it's the same as what it would have been if it was positive with a certain sign, right? And you could change the order of it when it was positive. Okay. So that's fine. And but what's another rule? Okay, so this is something other people definitely touched on that you would want to try to preserve. And I think there's one rule that really it's probably the most basic fundamental one that relates addition to multiplication, and that's like the distributive law, right? So distributive law is something that says, when you times two numbers, if you add two numbers and times it, it's the same as timesing them separately and then adding them. So for example, -1 times 6 is equal to 1 times 6 plus -1 times 6. So that's one special example of the distributive law. Okay, but it's meant to work for any numbers, any three numbers here. And you could sort of demonstrate for yourself the distributive law using an area, but then you'd have to only do that for positive numbers. And so actually, if you wanted to define multiplication on negative numbers so the distributive law holds, I'm saying that you really only have one choice. You have to make these negative times a negative to be a positive, and negative times a positive to be a positive. And actually, I've sort of saved some time to write this step. See, because what this left-hand side is, okay, it's 1 plus -1 times 6. So that's 0 times 6, which is 0. And the right-hand side is 1 times 6 plus -1 times 6. So it's 6 plus -1 times 6. Okay, so 0 equals 6 plus -1 times 6. And so now remember, that was the defining relation for what it means to be -6 or -6. So therefore, -1 times a number, it really is the negative of that number, provided this distributive law holds. And if the negative of 1 times a number is the negative of that number, then we know -1 times -1 is 1, and every negative number times any negative number will be positive, and so on. Doing that as a definition for multiplication of negative numbers, okay, allows you to maintain the distributive law. So let me quickly show you the distributive law. Should hold, I guess. For positive numbers, we can take it as a given. And anytime you have negative numbers, you have like say negative 6 minus 3 plus times negative 4. And we want to show that the distributive law holds. So what you do know... Yeah, sorry, we're showing the distributive... So now we've defined multiplication of negative numbers and positive numbers in the way we said before. So minus times a minus is a plus, and the numbers multiply the same. And minus times a plus is a minus. So if we do that, okay, the question is, does the distributive law hold for, say, negative numbers? And so, and the answer is it does. So if I could show this in a maybe more general way. So it holds for 6 plus 3 times 4. We know that. Okay, so that's equal to 6 times 4 plus 3 times 4. Okay. And because how we define multiplication, the left-hand side is the same as a minus of all this times minus this. So it's the same as minus times minus 4. And the right-hand side is the same as minus 6 times minus 4 plus minus 3 times minus 4. Okay. And so then this just becomes minus 6 plus minus 3. So I've used 6 and 3, but hopefully you can notice that the argument is rather general. But we've only done it for negative numbers. We haven't done it for combinations of negative and positive, but the principle should be the same, and a similar calculation should make it work. Okay, and that's exactly what the distributive law should be for this. So it should be minus 6 times minus 4 plus minus 3 times minus 4. Okay, so I guess in summary, we're taking minus x, so let's not use the letter x. We're taking minus a times minus b equals to a times b, and minus a times b equals to minus a times b and a times minus b equals minus a times b also as a definition. So we're taking this as a definition, and we're doing so with the hope I mean, with the need to maintain the fundamental rules of addition and multiplication. So there's distributive law and the commutative law, the swapping of things when you times. Okay. Yeah, and you can see the definition. They don't really overlap. Okay, so as long as you take care of 0 times 0, okay, this definition makes sense. We're defining exactly one output for every combination of inputs, and each combination of inputs with negative signs have not been defined before. Or negative numbers, sorry, have not been defined before, because we only had definition for multiplication for positive numbers.